Hi everyone, I'm Mitch W1SJ. I'm a very active contester, DXer, and public service operator. One of my favorite loves is teaching, especially about ham radio. Back in 1982, some 40 years ago, when I was pretty young, a friend said to me, "Hey, let's teach a class." I've never done that before, so I gave it a try. Well, my friend retired and moved to Florida, and silly old me, I've continued teaching the ham class ever since. Back then, things were quite different. The entry level license was the novice. You had to pass a 5 word per minute code test in addition to knowing rules and theory. There was no internet, and hardly anyone had a computer. The entry into ham radio involved picking up a license manual and perhaps attending a class. I had 30 or more people show up for class, but by the end of 12 grueling weeks of learning Morse code and other strange topics, the class whittled down to 5. But things have changed. The code went away, and the entry level license became the technician license. Computers and online learning has become prevalent. There are several ways to learn ham radio besides the old school way of picking up a license manual. I decided that it was time to bring teaching into the 21st century. Some 20 years ago, I started an online learning facility at hamclass.net. Students were now able to learn on their computer by accessing a website. There were narrated lessons, summaries, and review questions which offered corrections and actual online quizzes submitted to the instructor, that's me, which were graded and corrected. This online learning complemented the one-day technician and general classes I was offering in person. Now, instead of sending everyone a license manual that they didn't read, they logged onto the ham class site, and I could see the logins, and I knew if they were doing their homework or not. And in 2019, before anyone had ever heard of a pandemic, I decided to offer live video classes so that anyone, anywhere, could attend class and not have to travel to my location in New England. Classes are now offered online as well as via live video. And the live video class is every bit as good as a live class since you can ask questions and engage with the instructor in real time, and you don't have to travel. Our main focus today is to make everyone a more well-rounded radio operator. To be able to do this, we must never stop learning. We all start with the technician exam, and depending on your goals, move through the general and then perhaps extra. But you don't stop there. One is always challenged with learning new things. Consider that shiny new HF transceiver. Let's say you hit the jackpot and scored an Elecraft K4. Do you have any idea how much you have to learn to use this radio? The manual, if it was a printed one, would be the size of a Manhattan phone book. Heck, I've had an Elecraft K3 for 8 years and made over 5,000 contacts on the fool thing, and there are still things I don't know about it. And consider the lowly HT. There are still techniques to try which I have to look up in the book before figuring out what to do. You all have smartphones, don't you? Do you realize the time you spent learning which you had to do to find new and novel ways to waste time all day? I still need to go to school with my new phone as I'm pretty clueless about that. Fortunately, I simply say, "Hey Google, how do I do this?" And I usually get a correct, if not snide, answer. Sadly, though, teaching has gone down the toilet these days. Part of the reason is that folks want results immediately or sooner. As a result, instructors try to provide this demand, often with poor results. I once looked in on a technician ham class at a convention and was horrified to find it was nothing more than the instructor reading the questions and answers. As a college instructor, I find another disturbing thing where instead of teaching the syllabus, students are tasked with discussing their feelings on a particular topic. While this might work well for a book report, it serves no use in technical education. Finally, while sticking to the facts is always best, providing facts without reasoning will result in less learning. We must teach the what and the why. Too many educators today try to shortchange learning as an easy, fun thing like going to a theme park and let's have a load of fun. This falsely builds up the expectation of students to what will really occur. Let me be blunt. Learning new concepts is scary. Heck, it scares me when I start to learn a new concept. Humans have a natural fear of the unknown, but at the same time, humans have a natural curiosity of the unknown, which should overcome the initial fear. But there really is not anything to fear. I mean, really, the worst thing that'll happen if you fail your ham exam is that you just get to take it over another day. No big deal. Just don't tell anybody. If you fail to learn something today, be sure to learn it a lot better tomorrow. What I'm going to do in the next half hour is present you with ideas on how to learn new concepts instead of fumbling through. And I'll be clear that learning entails a lot more than watching a podcast or the latest YouTube video. That method will get you a short answer to a question or two, but the amount of useful knowledge you walk away with is limited. And why is this? Back around 1880, Hermann Ebbinghaus, he was a psychologist, developed a concept known as the forgetting curve. It is a mathematical expression which basically says that an average human will forget a lot of stuff they learn very quickly, like 30 to 50% of what they learn inside of 1 hour, and 50 to 80% in 1 day, and 90 to 95% after 1 week. Others have repeated this work and found nearly the same results. So here is the forgetting curve. Notice that we start here with time 0, and the amount of stuff you forget is dramatic very quickly. And here's the graph showing where you're forgetting about 50 to 70% right here. And by the time you get out to a week, you've forgotten most of it. If we factor in the degree of difficulty, stress, and lack of sleep, and lack of sleep often comes with classes, it gets worse. That means if I present you with 100 facts right now, in a day you'll only recall 30 of those 100 facts. Or if you're listening to a recitation of the 411 questions in the current technician question pool, you'll only recall 50% of those questions after 1 hour. And as you know, the passing score on the tech test is 74, not 50%. So how do you learn and retain? Ebbinghaus found 2 things which helps. One is mnemonic techniques, like ways to express things or pictures or ways to cement it into your mind. And 2, repetition based on active recall. Way back when, if you're kind of an old guy, kids often learn by repeating lessons over and over. We memorized the alphabet. We memorized multiplication tables. There was no calculators back then. We had to memorize the multiplication tables. Boring? Oh yes. But the trick for the teacher is to make it fun. We often made up songs or even cutesy sayings about the material. I like to relate personal stories about the things I was involved with which led to learning various ham radio techniques. Unfortunately, my students remember the story and not the material. Ultimately, I know that if I repeat each and every question and answer many times, that multiplied by the forgetting rate will come close to 100% recall. However, if I did that, the students would boil me in oil, which is hard enough to do in an online class. At the ham class site, I have students go through narrated slides. They see and hear the information, and that's important because some people don't read that well or don't retain very well when they read, so listening is also something that helps. I instruct them to repeat each slide 2 to 3 times and also take notes. The very act of writing something down is a way to engage active recall. Every so often, I have the students do review questions, which are the actual questions from the question pool. This also engages active recall in that now the student is seeing the same information presented as questions instead of statements. Eventually, the student takes the live video class where the same information is presented, this time in much more detail. So if we go back to the forgetting curve, you see we lose a lot of information in the first day. But if we add active recall, the more active recall we add, the slower you lose the information, you retain more information. So here, if you have a lot of active recall, you're not forgetting that much. And that is the key to good learning. So let's put these theories into practice here. I'm going to present a mini lesson on antennas taken from both the technician and general class syllabus. If you're an extra class, you might find this a useful review. And if you're not licensed and plan to learn the technician syllabus to get your license, or even if you plan to teach this material, you'll find this presentation very useful. I'm pretty sure you'll actually learn something new here. So we start off with antenna polarization. This is simple. If the antenna is parallel to ground, or if it's horizontal, it's horizontally polarized. And if it's perpendicular to the ground, it's vertically polarized. That's simple enough, but the trick is not to mix polarizations when communicating locally. If one station is horizontal and the other station is vertical, the signal may be attenuated as much as 20 dB or 100 times. It probably will not be this bad due to reflections, but it will be bad enough. So if you want to work repeaters, you need to be vertical. If you want to work weak signal single sideband, you need to be horizontal. There is an exception to all of this, though. If your signal is refracting off the ionosphere, in other words, if you are talking to somebody far away on 20 meters or engaging in 6-meter sporadic E-skip, you're bouncing off the ionosphere, the polarization gets twisted. The term we use for this is elliptical polarization. In this situation, the polarization of the transmitting and receiving stations does not matter. Another key topic is on feed lines. The feed line is very important because it needs to efficiently deliver your signal from the transmitter to the antenna and also efficiently deliver signals from the antenna to the receiver. The most popular feed line is coaxial cable. Coaxial cable consists of a center conductor, an insulator made of several different materials, a shield usually made of copper braid, and finally a black jacket to keep the moisture out. Why black? This reduces the damage due to ultraviolet radiation from the sun. Coaxial cable is easy to use and typically has an impedance of 50 ohms, which will match your transmitter output. However, there's a key downfall. This insulator here is very efficient at low frequencies, but as the frequency goes up, it becomes less efficient and it starts to convert your precious RF into wasteful heat. Typically 100 feet of classic RG8 or 213 cable, that's what this is. So 100 feet of that will result in losing half your power on 2 meters and almost 2/3 of your power on 70 centimeters. And it can get worse. We'll soon talk about SWR. If you have SWR, the loss in the coax goes up even higher. So the prime directive with feed lines is to keep feed line length as short as possible and keep the SWR low, or else you'll have to use larger and more expensive hardline cable or open wire line, which has less loss. Now, we can make coax out of flexible copper pipe with plastic spacers holding the center insulator in place. Well, the insulation is essentially air, and air is virtually loss-free, but there's a catch. One needs to keep moisture out of the cable because that will cause loss, and this is done by pressurizing the cable with nitrogen. Air-insulated hardline coax is very efficient, but only broadcast stations use it due to the requirement to have a nitrogen bottle hooked in. Another method to attain loss-free feed lines is to use open wire line. There's an open wire line. This is 2 wires spaced a half an inch or an inch apart with these spacers. However, the insulation is air, and so the cable is very efficient. And so, by the way, we call it ladder line because it looks like a ladder, right? But this line must not come near ground or any metal objects. It's hot, and you better not touch it when you're putting 100 watts into it. You're going to know it. Also, the impedance is a 300 to 450 ohms and it's a balanced feed line. Therefore, a special device called a balun, there is a balun, is used to match the impedance, the high impedance of the open wire line that connects here to the lower impedance and the unbalanced output of the coax. We cannot talk about feed lines without mentioning connectors. There are many connectors out there, but hams focus on three types. The first is the UHF connector, also known as the PL259 connector, which is an all-purpose RF connector. And here's what it looks like, side view. Here's what it looks like front end. You notice a big fat insulator there, or big fat center conductor in the middle. This connector is not very good at UHF, and so just to confuse everyone, it is misnamed the UHF connector to drive students of the technician syllabus crazy. For UHF and above, we instead use the N connector. There's the N connector, and there's a look inside. So the center conductor is very small, very thin, and there's a shield around it inside the shell. This is a very efficient connector that can be used at very high frequencies. And finally, there is the SMA connector, which is a very good connector, similar to the N. You see it's very, very tiny. There's the N by comparison. And it's perfect for use on handheld radios and other small applications. And finally, when using parallel conductor feed line, we don't use a connector at all. The wires are just connected to screw terminals. A transmission system consists of a transmitter, feed line, and antenna. The impedance of all these items must match, and they have to match the transmitter, which is always designed to be 50 ohms. If there's a mismatch, this will result in something called standing wave ratio. What happens is your signal goes up to the antenna, and some of it gets radiated, and some of it gets reflected back down the line to the transmitter, and then it gets retransmitted back up. So you got signals going up and down this feed line. And we're going to end up with something called standing wave ratio, or SWR. If everything is matched, the voltage along the feed line and antenna is the same. Whatever the voltage is, it's the same. But with SWR, we literally get standing waves on the feed line. We see, if we could see voltage, which we can't, but if we can see voltage, we'd see these little loops of high voltages and low voltages. So for example, if we have an SWR of 2 to 1, it means the maximum voltage is twice the minimum voltage. So SWR does a number of bad things. First, less signal is radiated. Second, higher voltages are found on the system, and this might cause you problems. And finally, your transmitter hates this and will get really mad at you and destroy itself, resulting in a repair bill of hundreds of dollars. Transmitters do have protection circuits, but don't rely on this. You should keep your SWR lower than 2 to 1, and you can do this either by using a resonant antenna or using a properly adjusted antenna tuner in the system. So how do we know what SWR is? Well, we use an SWR meter just like this. I got this from when I was first a ham 52 years ago, right? It's a really cheap SWR meter, but it works. You put the power in here, you get the power out of there. Or if we want to get fancier, we use a directional watt meter like that, where we can measure power going up to the antenna and measure power going back from the antenna and calculate the SWR. Now we're going to jump to the general class syllabus, and we're going to go into a little bit more detail about antennas. We'll first look at the dipole antenna. And the dipole antenna consists of a wire cut and fed with feed line somewhere in the middle. So here is our dipole antenna, just like that. You see the feed line in the middle. It doesn't have to be in the middle, but in this case it is. Now the half-wave dipole is about a half wavelength long. I just have this short so you can see it on the camera. And this antenna has the good fortune of having an impedance of 73 ohms in free space. Free space meaning that it is far enough away from any structures or the ground or the earth so that it's not affected. So 73 ohms is pretty close to the 50 ohms our transmitter would like to see, and it works fairly well. And a dipole radiates in a figure 8 pattern, which means that the maximum energy is going towards you and going towards me, and minimum energy is going to where my fingertips are. So the length of a dipole is calculated by taking 468 and dividing by the frequency in megahertz. Now remember, the length increases as we go down in frequency. It's opposite. So a dipole on 2 meters, 146 megahertz, it's about 3.2 feet long. Okay, not that bad, right? A dipole for 14 megahertz or 20 meters is about 33 feet. But if you want to get on the top band, 160 meters, a dipole for 1.8 megahertz is a whopping 260 feet long. That's what's required. Now we can do all sorts of things to a dipole and it will still work, but the impedance will change. So one thing we can do is we can hang the dipole from a high spot like a tree and bend the elements down like this. Okay, so the elements are coming down. If I get this to behave, and this is called an inverted V dipole. There we go. I don't need the high hook anymore, inverted V. Now what that does, the antenna radiates pretty much the same, but the inverted V will have a 50 ohm impedance and will be in perfect match for your transmitter. Or if you need to put the feed point near the end of the dipole because you cannot reach, so let's say this is your dipole here and you're feeding it from the end, you can do that too. However, the impedance jumps to a very high value, so you have to provide proper matching. Or we can make this antenna longer than a half wavelength. Okay, we can make it many wavelengths long, and that will actually give you gain. Okay, but it will change the impedance radically. And again, if the impedance is not around 50 ohms, we need to provide a matching network to allow the transmitter to work. So we use a transmatch. A transmatch is a matching network. And you think of a transmatch as cocaine for transmitters. It really doesn't change the impedance of your antenna system. It simply makes the transmitter think it is seeing 50 ohms and it is happy. It's very pleased, and so are you. So the height of an antenna, any antenna, is important. Near the ground, the perfect figure 8 pattern becomes distorted due to ground reflections. A dipole close to the ground, less than a quarter wavelength high, it will radiate straight up. Okay, so if we're close to ground, this is going to radiate straight up. And a dipole around 35 feet up on 40 meters, that's about a quarter wavelength. That'll fit the bill. It's great for working people in your immediate region, but not so good for working people far away. However, when a dipole is really high, like 1 wavelength or more, which we're talking now 120 feet on 40 meters or like 70 feet on 20 meters, the radiation, instead of going up, goes out, goes almost to the horizon. And that is the best direction for working DX. And this is why they say that if your antenna did not fall down last winter, it ain't high enough. So let's try a review. Let's make sure we learn everything here about the dipole that we want to learn. And pay attention because we're going to ask questions at some point here, right? So here's a pictorial of the dipole. So the line is broken in the center here. That's where the feed line comes in. And this length is 468 divided by the frequency in megahertz. The free space impedance is 73 ohms. However, if we bend the dipole so that the top is high, it becomes an inverted V and the impedance goes to 50 ohms. Or if we feed it from the end instead of the middle, the impedance goes very high. The pattern is shown in this figure here. It's a modified figure 8. It's not a perfect figure 8 when you're close to ground. It's a modified figure 8, so it's best broadside off the antenna, not so good off the ends. It's not that bad. It's really only a half an S unit weaker. Not tremendously bad, but it is a little weaker. And here's the vertical radiation pattern of a dipole. If you're a quarter wavelength or less from ground, it radiates essentially straight up. Okay, that's straight up. And straight up is good for talking to people a few hundred miles away. Not so good for working DX, which is down here. When you raise that dipole antenna up, the pattern goes lower and lower. Here, this is probably a good antenna for working California maybe. And if you put it even higher, it'll even get better for working further away. So that is what a dipole is. Those are some of the characteristics that we need to pay attention to. Now, let's take our dipole antenna and we're going to do something interesting. We're going to hang it vertically like this. Okay, so here's the dipole hanging vertically, and it'll work just like a dipole. It'll radiate better to low angles than to high angles. Okay, so you need like a big high tree to do this, of course, but this is what we can do. Watch this. We could take the bottom half of the dipole and bend it like this, forming what's called a radial. And this is kind of like an L antenna, right? And you'll end up with a quarter wavelength vertical antenna. This is the radiating part of the antenna. So such an antenna has a characteristic impedance around 35 ohms, which is close enough to 50 ohms. Now, if you bend the radial down like that, you'll push the impedance right up to 50 ohms, which makes it like an inverted V. So the good news is that this antenna is half the length of a dipole. It's only a quarter wavelength instead of a half wavelength, right? But here's the catch. You need multiple ground radials, okay? So you can have elevated radials. You need at least 3 or 4 of these radials going out. Or if you mount this thing on the ground, ground is not a very good ground, by the way. You have to bury a lot of wire, usually between 30 and 60 wires into the ground. Otherwise, the antenna is very lossy. You'll hear people on it, but they're not going to hear you very well at all. And you can also make this antenna longer than a quarter wavelength, and it will radiate further out. So thus, a lot of people on 2 meters use a 5/8 wave whip. That makes the antenna radiate better down the highway instead of up in the sky. Now, if you go mobile and you're operating, let's say, on 20 meters, a quarter wavelength antenna for 20 meters is going to be 16 feet high. Well, that's not going to be good. That's going to be an issue with overpasses, right? So what we do is we use a shorter whip, like 10 feet, and put a loading coil in there to make up the difference and to tune it to 50 ohms. But when you do this, the antenna is less efficient and only works over a small range of frequencies. Now, finally, we're going to talk about the beam antenna, or Yagi. So this is what happens with the Yagi antenna. Now, so the Yagi antenna, normally it would either be horizontal like this or vertical like this. I'm going to hold it like this so we can actually see what's going on in the camera. So this Yagi is pointing straight up. This is good for talking to people on the moon or satellites. Normally you'd put it down towards the ground. So this is a dipole antenna right here, 468 over f. Now, if we put a slightly longer element here on one side of it, what that will do will be to force more radiation away from this element. Force it this way, okay? And then along the same lines, if we put a slightly shorter element here, the slightly shorter element will force the radiation towards it. So if it's longer, it goes away. If it's shorter, it goes towards. The longer element's called the reflector, the shorter element's called the director, and the element in the middle, the dipole, is the driven element. So named because that's where the feed line goes. No feed line goes to these other elements. They're parasitic. They go along for the ride. They're important, but they go along for the ride. So the reflector is 3% longer than the driven, and the director is 3% shorter than the driven. But we don't need to stop at 3 elements. We can add more elements, and this thing here that connects everybody, this is called the boom. We can make this boom longer and longer and longer and have a lot of elements. I have an 11 element antenna, a 15 element antenna, a 25 element antenna on some bands. These are monsters. I don't have them in here because you'd never see them on the camera, right? But that'll even give you more gain and more performance. So when we compare the extra signal we get on both transmit and receive to a reference like a dipole antenna, for instance, this is called the gain, and it's measured in decibels. So this 3-element Yagi will have a typical gain of 7 dB over a dipole. That's just like increasing your power 5 times. The gain comes not from the transmitted signal. It comes from, I mean, you're using the same amount of power, but what happens is you're reducing the power going behind the antenna and you're reducing the power off the sides. You're literally squeezing the signal out towards the front. Think of a tube of toothpaste. You squeeze all sides of it and it comes out in the one direction where the cap is left off. And hopefully you have something to catch the extra toothpaste in, because toothpaste is more messier than RF. So the main signal here is called the major lobe. There's a little smaller back signal called the minor lobe. And one of the ways we measure the antenna is the front to back ratio. You want to have a lot of front to back ratio and you want to have a lot of gain. So this is great. Not only do you get gain, it can minimize interference. For instance, if you're getting interference from Europe and you're pointing the antenna this way, right? That's at my house, that's towards Europe. And somebody's bothering you, whatever, you turn the antenna around and point it this way towards the US. And the noise and interference from Europe magically goes away. And of course, vice versa too. If you want to get rid of someone from the stateside, you can point it from Europe. So a Yagi wants to have good gain and good front to back ratio. So our Yagi has an impedance around 100 ohms. So that's a little too high for 50 ohms of our transmitter. So we use a simple matching system called the beta match or gamma match. This is the beta match here, right? The gamma match is good because the elements do not have to be insulated from the metal boom. Well, I'm using a wooden boom, so I don't have to worry about that. That's why I'm using a beta match. But the gamma match is great for all metal antennas. So let's review the Yagi information to make sure that we all got it here. Okay, so here's our Yagi. Here's the driven element, which is basically a dipole, 468 over F. Here is the reflector. It's 3% longer. Here is the director. It's 3% shorter, and your radiation is in the direction of the director. So if you want more gain, you add more elements, and you add more boom length. The Yagi impedance is around 100 ohms, so you need a beta or a gamma match to match it to 50 ohms. And here is the radiation pattern of a Yagi. So here's your major lobe. Look how much is going out this way. Look how much is going towards the back. Now a dipole will radiate better than the Yagi in the back, but it won't radiate as well to the front. So that Yagi has to be pointed in the right direction. So this is a great start to the general class syllabus on antennas. There's more information to be learned here, but we're running short of time. But you can go to hamclass.net and log in and continue all the lessons for both the technician and the general. So let's talk about learning again. How do you find answers to your questions or learn new ideas? I'll tell you that the worst method is to post a question on a reflector or ask on a repeater. If you ask 5 hams, you're likely going to get 5 or more different opinions, and some of them may be plain wrong. Realize that hardly anything is black and white in technical discussions. There may be nuances in the technical situation which require a back and forth exchange to determine exactly what it is you want to do and what to learn. So texting and emailing, that's just not going to work. Okay, it's a good place to start, to introduce the topic, but you have to have plans for further two-way discussion. You really need to talk to somebody. I found that identifying one or more technical experts in your area is best. These are the people who have proven time and time again that they understand a lot of technical concepts and know what questions to ask you so that they can focus in on the correct set of details. Such people also know when to say, I don't really know, instead of giving you a vague or even wrong answer. But what if you need an answer now and your technical guru is not available, or else you cannot even find anyone in your area with significant technical prowess? You then have to engage in research. I'm a trained electrical engineer. Now, that doesn't mean I know more stuff than everyone or that I'm even smarter than everyone. Instead, I have learned to find the answers I need and vet those answers so that they make sense. Anyone can do research in finances. You have to be willing to put the time and effort into your search. Knowledge doesn't fall from trees. You have to do the work. Years ago, that meant spending hours at the library going through the card catalog and finding books which covered the material in question. Today, it's much easier to do an online search, but you'll get more input than you care to get, and some of the responses will have nothing to do with the specific topic you're looking for. You have to be savvy in the words you use to search so that you can whittle down the search to the best 5 to 10 sites. Also realize there are different search engines out there. Some base their searches on how much advertising a client provides. Other search engines are downright biased and block content they don't want you to see. So you have to try different searches on different engines to finally arrive at sites which might provide you with the learning you desire. Oh, by the way, just because a site's on a search engine doesn't mean that it's necessarily correct. There's a lot of nonsense out there. Be sure to visit several sites and thoroughly go through what they are presenting. If you're watching a video and it's specific to your question, watch it a few times and take notes while viewing. Remember, you only retain 30 to 50% of what you're exposed to. You will eventually find a number of sites saying pretty much the same things, and perhaps other sites saying things which are either more controversial in their approach or just plain wrong. But beware of sites offering opinion in place of facts. Opinions are fine for an interesting discussion with a pal, but what you really want is long proven scientific facts. So whether you're looking to get your first license or looking to upgrade or looking to build a better station or build a better antenna, you need to continue to keep learning. If you keep doing the same old stuff over and over again, it gets boring. Be sure to learn new concepts and techniques. The field of amateur radio is virtually endless if you keep exploring. Learning is a lifelong process, which should always be going on while you're living. So I'll join you shortly for the question and answer session. Otherwise, contact me at W1SJ at ARRL.net or go to my site, hamclass.net, and you can contact me there. 7-3 from W1SJ.